Hello viewers, today we are going to study about experimental study of photoelectric effect. This is the basic experimental arrangement for study of photoelectric effect. You have a evacuated glass bulb and a quartz window where we allow the light to strike the cathode. The cathode is made up of photosensitive plate and the anode is connected to positive and the cathode is connected to the negative. To see the current, photoelectrons, we use a microampere meter and a voltmeter to see the potential difference between anode and cathode. This is basically a commutator, that is, you can make anode positive and cathode negative, or if you want to change, you can make this as negative and this as positive. So the basic idea of this setup is you have a fixed supply, say 10 volts or 20 volts, and you want to vary this. So for that you use a variable resistor. So now if you take the voltage between these 2 points, you can vary anywhere between 0 to 10 volts. If it is going to be 20 volts, anywhere between 0 to 20. That means at this point you will get a varying voltage. Regarding the commutator, you have this is cathode, this is anode. So you can make this positive, negative to take one type of measurements, and you can make anode negative and cathode positive to take other type of measurements. So that is the provision that is given here as commutator. To see the voltage that we are giving to between anode and cathode, we connect a voltmeter to see what is the voltage we are applying between anode and cathode, and to see the photoelectrons we connect a ammeter in series. So we have this microamps meter to see the current. That's the idea of this diagram. So this is a variable source, we can see the voltage, we can see the photoelectrons here, and the commutator is a provision by which we can make anode positive, cathode negative in one type of measurement, or we can do the other way, cathode positive and anode negative. So first we are going to see the effect of intensity of light on photocurrent. Okay. Now what we do is we are increasing the intensity of light. Correspondingly, photoelectric current also increases. That means initially assume the distance here is some light source. Assume the distance between the cathode and this one, say 1 meter. Once it crosses, the light is allowed to hit the cathode photosensitive plate. Already we have biased this cathode and anode. Assume this is positive and negative with this supply, variable supply. So once it crosses the work function of the photosensitive metal used as cathode, the electrons, because of light, the electron starts moving. So these electrons strikes the anode and there is a current in the circuit. To measure the current, we have connected a microamps meter. We can see the intensity of the current in this microamps meter. So now what happens is intensity, this is one reading. Another reading will be you move this source slightly towards the cathode. Now the distance decreases, but the intensity of the light is same. So in that case, more number of electrons will be released from cathode and it travels toward the anode, and there is an increase in the current. Similarly, without changing the intensity of the light, if you keep on decreasing the distance, the photoelectric current increases because the intensity of light increases. So you see a linear relationship between the intensity of light and photoelectric current. Okay, so intensity of light increases, photoelectric current also increases in a linear fashion. Here we are not altering the frequency of the source. Okay, that you have to keep in mind. The frequency of the incoming source is not at all altered, it is same frequency. Only we are changing the intensity of light, thereby we are measuring the photoelectric current. Okay, this is one observation. The second one is, so this graph is about collector plate potential. If I say collector plate, it is anode potential and the photocurrent. What is the relation? So here what we do is, this is for intensity 1, intensity 2 and intensity 3 of light. So we are dealing with 3 different cases. So when voltage is 0 between anode and cathode, there will be some photocurrent because of light source with intensity 1. The photocurrent is slightly increased if the intensity also increases, and if intensity increases, the photocurrent also increases. This is above, actually if you see there is some small rise. So afterwards it is a photocurrent is constant because of the different intensity of light. If the intensity is more, I3 is greater than I2, which is greater than I1, therefore photocurrent also is greater in these cases. Now suppose we reverse bias the anode and cathode, that is anode is given with a negative and cathode is given with positive. So we are supplying with a negative voltage or retarding potential. So if you keep on increasing, there is a decrease in photocurrent, but all will reach at one point, say we call it a stopping potential, where the photocurrent is 0. That is, you can reverse bias the anode and cathode. The anode is supplied with negative and cathode is supplied with positive. These the current, photocurrent slowly decreases in all the 3 cases with 3 different intensity of light and reach at the same point, which is called the stopping potential. This is important because even though the intensities are different, the stopping potential for all these 3 cases with the same frequency, these 3 sources have the same frequency. Only thing is we are changing the intensity of the light. When it is forward biased, we have a photocurrent that is depends on the intensity of the light. If the intensity increases, photocurrent also increases. But once you reverse bias, that is anode is given negative, cathode is given positive, you are reverse biasing, all the 3 shows that the stopping potential is same. Suppose if I say this is minus 20 volts or minus 10 volts or minus 3 volts, for all these 3 intensity of light sources, the stopping potential is same. In this experiment, we are not changing the wavelength of the incoming light source or the frequency of the incoming light source. Okay, next is here the another graph. This is about collector plate potential, photoelectric current. Variation of photoelectric current with collector plate potential for different frequencies of incident radiation. Now we are dealing with 3 different frequencies. That is frequency 1, frequency 2 and frequency 3, or we can tell in terms of wavelength also, lambda 1, lambda 2, lambda 3. So collector plate potential, if you increase, there is an increase in the photoelectric current and all the 3 wavelengths will saturate at one point, and we call this as saturation current. Whereas the anode and cathode is reverse bias, you can see that the stopping potential, or where the photoelectric current which is 0, It depends on the frequency. See, F1, F2 and F3, the stopping potential for this first case is say minus 1 volt. The stopping potential of F2 is minus 2 and stopping potential of F3 is minus 3. This is just an example. That means it is not same. But in the previous case what we saw is the stopping potential, if the frequency is same, will reach only at the same point. Since the frequency is different, the stopping potential is also different in the reverse bias condition. Whereas in the forward bias condition, all these wavelengths reach at one point called saturation current, where the photoelectric current is going to be constant even though the potential difference between anode and cathode keeps on increasing. So that is the point we have to remember in this case. Next is we have frequency of incident radiation. Now x-axis we are taking F frequency or nu, and here we have stopping potential. Now we deal with two different cases, metal A and metal B. Now if you take metal A, there is no initially the frequency of incident radiation. Here it at nu naught, only above this frequency the stopping potential keeps on increasing for metal A. Linearly it will increase. For if you consider with another case, say metal B, from this 0 to some threshold frequency, we call this as threshold frequency, there is no stopping potential, it is 0, but afterwards when you increase the frequency of radiation, it keeps on increasing linearly, so stopping potential also increases. That is, the point I would emphasize is up to some threshold frequency the stopping potential is 0 for metal A and for metal B, whereas for metal A the threshold frequency is nu naught and for metal B it is nu naught dash. But for metal A, once you cross this nu naught, when you increase the frequency, the stopping potential linearly increases with frequency. Same thing happens with metal B also. So from 0 to nu naught dash, this is called threshold frequency. The stopping potential is 0. Whereas after crossing nu naught dash, the threshold frequency, metal B, the stopping potential, if you increase the frequency, the stopping potential also increases. Okay, so these are some of the important observations we have to consider, and these have been proven. And when we conduct lab, these three experiments are important to study the characteristics about photoelectrons of different types of materials operated with different types of frequencies. Hope you have understood about this experimental study of photoelectric effect. I told you anode and cathode, which can be positive and this is negative, so forward bias, so electron, then you can make this as negative and positive. So we have dealt with the intensity of light, stopping potential and its effect with the different frequencies. So that's all about this topic about experimental study of photoelectric effect. Hope you have understood this topic thoroughly. Thanks for watching. Nandri.